Good morning, everyone, and thank you very much for coming. We are, for those of you who don't know us, I am Professor Eleni Bosia from the Department of Classics, and this is my colleague Angelos Barmpoutis from the Digital Worlds Institute. And we are going to take you on an introduction to 3D data acquisition and dissemination. Several people have been talking over the past few years about 3D data, why is it important, why do we do it, how do we do it, and why do we do it. So we decided to put together this presentation in which we are going to give you a brief introduction into 3D data and also hands-on opportunities. We brought some of the technology that we are currently using and technology that we used in the past so that you can get an idea about what is 3D data, but also how can you do it? How do you decide what sort of artifacts you have? How do you go about working with 3D data? So instead of just giving you a lecture, we decided to give you the opportunity to have some, even if it is primary experience with 3D digitization. Now, the reason why we are presenting this and why we are doing this together, we are the the director and the associate director of the Digital Epigraphy and Archaeology Project, which is an international association for the 3D digitization, dissemination, preservation, and enhanced automatic analysis of archaeological artifacts. We started and we established the DEA project back in 2007. So this is our 11th year. And we started with the 3D digitization of copies, paper copies, of inscriptions. We started with ancient Greek and Latin inscriptions, since I come from the Department of Classics. So it was, that's why I wanted this, and we wanted this not to be a lecture, but to be kind of a collaboration with you, because the way we got into 3D digitization was through personal needs. We were working, we had our own data, and it was our own desire to do something else that led us to the discovery and exploration of 3D technologies. So having started with paper copies of inscriptions, which we actually digitized using a regular office scanner, and I'm going to show you pictures of the scanner and our website online. We decided also to continue exploring other archaeological artifacts that were 3D, so not just paper flat copies of inscriptions. So when we started expanding onto statues and vases and other artifacts, we also had to start exploring other 3D digitization techniques. Which, again, was another reason why we wanted you to go through all the processes that I'm going to show you through the slides to see that different needs and different data lead you to different methods. It's not always the most expensive one that will help you do what it is that you want to do. It's not always the most complicated one that is going to be the answer to your needs. We have, lately, we have also been exploring and working with virtual and augmented reality. So we are going to, you have the, yes. So you're going to have also an idea about the next step. So after we have and we can deal with and manipulate and analyze 3D data, what else it is that we can do with it? How else can we recreate another physicality for our 3D data?
Of course, this is a very practical subject that involves 3D data, and some of you may say, well, in my discipline, I'm, let's say, I work in literature, and obviously everything is in pen and paper and printed material, so I don't have any 3D actual content on my discipline, and I don't have anything to digitize. But you may be wrong. Recently, we formed a collaboration with the Library of Congress that they had letters from Abraham Lincoln, that they had actually an imprint on an embossment on the top of the letters that was not legible. The 3D surface anaglyph of this embossment was not legible. So what we did basically, we used some of these methods to analyze it in 3D, enhance in 3D the model, and be able to decipher exactly what the anaglyph says, and which was a particular printing house at the age of Abraham Lincoln that actually had some sort of commission with White House back then. So 3D is not necessarily a big 3D object. It could be something that has a small, insignificant, very tiny detail, but which is worth exploring, like the surface of a coin, the surface of an embossment. And of course, we will also show you how to actually digitize with some of these technologies an actual physical 3D model. And for the purpose of the demonstration, we brought with us a replica of the top of an ancient pillar.
So let's get started, so that hopefully you will have time also to play and use some of the technology that we brought. Excuse me. We decided to divide this introduction to 3D technology into the different types of 3D tools, which will also give you an idea about the different methods, digitization methods. So one is how do you create a 3D? By creating shape from stereo. If you have a stereoscopic camera, which would be basically two cameras, and how does the 3D shape, how is it captured? It is it basically calculates the displacement of each point as it is captured from the two different cameras. And, sorry? Another way to digitize in 3D is shape from motion. So basically what it does is it calculates the depth, the 3D shape, in other words, by calculating the displacement of the point, but in two consecutive frames. So similar idea, but different execution.
About that in practice, recently we had different apps in phones that basically what they did, they allowed you to take a video or a sequence of pictures, and in this slide, for instance, you see that the subject goes basically around this object here, recording the video, but in real time, it reconstructs in 3D the surface of this object, not only for the 3D digitization purposes, but also to superimpose an object. And this is basically what led to augmented reality applications that later in the day you will see by Sarah. And this, of course, technology that we now every day use, we may use in our smartphones, was developed several years ago. And this example is from the early 2000s, actually 2000.
We actually explored this possibility of working with something like this when we started back in 2007, trying to figure out how we can digitize in 3D our copies of inscriptions. However, one of the major disadvantages, at least for the data set that we were working with back then, is that it cannot capture small details. So when you are talking about, you can capture, let's say, a column, and it will do a very good job of 3D reconstructing it. However, if you are talking about a centimeter or a millimeter big letter, then you need something that is a lot more detailed than this. So even though it seems easy, it's relatively intuitive to do it, and it works. But again, it depends on what it is, what is your object.
One of examples, for instance, of popular iPhone apps, and I think it was also available in Android, which was recently though, discontinued, was developed by one major major companies in this area, Autodesk, and they created basically this algorithm in an app called 123D Cats, where you could actually move around the object, and they had a demo online with this small replica of a dinosaur model where you could actually take pictures around it, and they guide you basically how many pictures to take, and on the top of the object, around the object, and at the end you could actually blend the 3D model with the colors of the picture that you were taking. So it's not just the 3D structure of the model, it has the colors and the texture, and it feels real. Of course, as Eleni said, this method does not capture the details, and that was the major criticism of this particular software. You have to take many pictures, which is a cumbersome process and takes could take an hour if you want to capture all the views of a model. And of course, there are better ways to do it, even with smartphones nowadays, if you add some additional hardware. And this is what we will present you after that.
We actually used this particular app last year. It was the last time that we used it in class. And it had several problems additional to the capturing of details. When you were trying to do a very accurate model of something, so you would take more pictures, it would get stuck, and it wasn't able to process them anyway. So it had several issues that my students encountered in class. Now, one that we are going to demonstrate you with technology that we have with us, it's shape from structured light. So basically, the camera projects a particular light that captures the shape of your object, and the shape is described by the deformation of the pattern of the light that is projected. We have actually used, and we have an example, we brought it here with us, we actually used Artex 3D scanner that utilizes that particular technology with the structured light for that particular artifact that we digitized in collaboration with the Museum in Tampa, the Museum of Art in Tampa. As you can see, it was relatively accurate at the time. Limitations that it has is that, first of all, you need to be careful that it won't capture anything that it is black, anything that it is particularly shiny, which makes sense since it projects light. It will not reflect, or it will reflect too much on something shiny, so it will be unable to capture the surface, the 3D surface.
Everything about 3D scanning is very practical. And if you create a situation that is an optical illusion for us, definitely it will confuse the computer even more, which is not as smart as we are. So black surfaces, we cannot understand if it is a black opaque material, we cannot understand the structure as if it was like a white, where you can see the shading and you can derive the shape from the shading of this material. Most of these technologies use some sort of projection. So here, what this device has, it's a light source down here that flashes very frequently, and it flashes not just white light, it's a particular structured light that creates a grid. So there is an actual black grid among the pattern that this device flashes. And what it does, it has two cameras, you can see, so stereoscopically, as we do, can observe those points, those patterns, the lines that it flashes on the surface, and depending on how the lines are deformed on the object, it deducts the actual 3D geometry. So you have to flash, basically, and move around the object, and it flashes, and it does, it collects, accumulates points by points, and at the end, you try basically to merge the collected information into one solid model.
Advantages is that even compared to the, discontinued for now, but the taking pictures with your phone, is that it is a lot faster. Even back then, even though it is an older technology than what we are currently using, but you literally walk around the artifact and it creates the 3D shape. So from that perspective, it's it was more useful to us. One thing to keep in mind is that with all these technologies, even the ones that they are projecting light, you can assure whoever it is that you're working with that they are not, the light is not hurting the artifacts. It's not invasive in any way. A disadvantage that they have, and it may seem very minimal, but if you are working in a museum, it is actually a big disadvantage, is that it needs to be plugged. So if you can find something in a museum, you don't always, yes, you are smiling, but you can't imagine what it is. If you go through a process of applying for a grant, you get the grant, you travel, you get the license, permits to work at a museum, you go there, and there is nowhere to plug your 3D scanner. So it is an actual issue that we are not facing now with the structure sensor that we are going to show you later. So 3D digitization has, like Angelos mentioned, some practical issues, not only with respect to how it works, but literally practically if you are undertaking a project, a field project.
This is an example that they provide. Actually, they scanned this minivan. I believe it's Volkswagen, the popular model. So they actually went. They spent a significant amount of time. They went around the vehicle and they captured the details. But of course, this is the result of post-processing as well. So don't get the impression that you move around the object, a bigger object or a smaller object, and that's it. You get instantly a model. No, you have collected all these points that may form a noisy pattern. You have to actually do some post-processing. They provide the software to do the post-processing, which depends on how many points you have collected in total. It tries to accumulate them in a meaningful shape, and that could take hours as well, the post-processing. So the collection is instant, but to go to this, to reach this final like stage where you have a nice refined model, this may take several post-processing steps.
Another project in which projected light was used was this one, and I believe that you're familiar with both the person and the bust.
And the same company basically creates these scanners. So this is the current version of the scanner. This is a slightly older version of the same technique. So what they did basically, they created the realistic, because it is based on real data and real 3D data, the bust of the former president, and I believe this is the one that decorates now the area on the White House that has the busts. So should we do the demo first?
Sure, yes.
Yeah. So let's see if this works. Okay, so this is just a preview in the beginning to set up basically your workspace. So what I do here, I move the camera in this preview mode so that the little histogram that is shown on the left-hand side here, we have like a plot, a vertical plot, as you can see. It shows where my points are, how far my points are. So if I move far away, you see all the points are on the top of this diagram. If I move too close, all the points go down on this histogram. So the idea is to optimize the scanning by moving the camera somewhere in the middle distance, which is the optimal distance for this projected light. Now, I'm not sure if the camera will be able to show you the projected light, because it's bright. So I mean, it is a flashing pattern here. There is some like insignificant sometimes with the naked eye to see that there are actual lines projected. Maybe but what I'm flashing now, it's an actual pattern with lines that the cameras here observe. So the idea is to move around the object. So once I set up my workspace and I establish the optimal distance from the object, I can press the button here as if I was taking a picture. And what you are actually taking, it's a video, if you will. It's a collection of those 3D frames. So I press the button here, and the view has slightly changed the colors, and I move gradually around the object, as you can see. And I can move it on the top of the object. And of course, it creates, as I said, this noisy pattern that some of these data may be overlapping, erroneously overlapping. So there is a mechanism at the end to clean up the data, and I'm not going to spend time to actually scan all the sides of this object, so I think you got the idea how this works. So I have this very noisy cloud. So assuming that I'm happy with this with this model, so it is noisy. It doesn't make any sense. So what it is, it's an accumulation, basically, of all the consecutive points that I collected. Of course, if I had spent more time, I would go on the other side, on the top, and on the front side, and I could have collected data from all these orientations. And of course, you can see here that part of the podium was also captured. So there is a sequence of steps over here that are provided, which is basically the registration, a rough serial registration. There is a very fine spatial registration that takes more time, as you can see. So here, there is a progress bar on the bottom that performs. Now, some of that has been aligned, better aligned here, so it is less noisy, but there is an even more time-consuming step, which is a global registration. So in order to create the global object, you can align everything with respect to all the others. I'm not going to press that button just for to move on with to other techniques, but I'm going to do the fusion, which is the final step that detect basically all the different orientations, and it takes some time, and it fuses the 3D points into a solid surface. So instead of having a cloud of points, as it is shown here, we have an actual surface, and depending on how much time I spend, the surface may look again noisy or not. So in this particular case, some of these parts have been successfully scanned, some others are noisy. So it depends basically on how much time I spend and how optimal is my distance. But I think this, and actually this is not the actual result. We are step 3 from 3. So in a few seconds, hopefully, we will see the result from this very rough scanning session. But as I said, it takes time to adjust yourself, and to, of course, you need to spend more time to actually perform a better scan. So I believe that's the rough approximate surface that this created. As we all agree, is not satisfactory at this point, but spending more time and optimizing your scanning area, including external light sources. So for instance, on purpose, I didn't go significantly from the front because we have other intense light coming from this side, which attenuates the pattern of this scanner. So there are very practical aspects that we have to take under consideration. So most of these scanning techniques could have some negative effect from the sunlight as well. So imagine if this light is considered intense, scanning something outdoors may have similar problems.
Do you have any questions before we move on? Comments, anyone? Everything makes sense so far? Yep. Now, another technique for 3D digitization is laser scanning. So basically, the rough description would be that the 3D shape is being reconstructed as by actually calculating the time of flight. So the time that it takes for the laser to go to the point and come back. This is basically how the technique works, and Kinect One is using that laser scanner technique. We have actually used Kinect One ourselves on a project that we undertook with Palazzo Altam in Rome in 2013. in which we digitized their entire collection of StatHue. So it was when we started in 2012 exploring options for StatHue 3D digitization, and Kinect One was the answer to our problem, and we started with that. I'm going to show you how it works, and I also have on the PowerPoint our results, so you'll get to see and judge by yourselves. It is fast, it's accurate, it's easier to use than Artec that Angelos just showed you. The problem, still the limitation, is that it still needs to be plugged to the computer and plugged by itself. Are you going to do that first? But the results were fairly accurate, you'll see. The process that we follow is exactly the same as with the Artec scanner. You are basically walking around the artifact. You need to capture the top, which again, when you are talking about a StatHue that is already prompted up somewhere, it's very hard to capture. Usually, for some of the StatHues, we don't have the top of their heads because we couldn't quite reach, and they wouldn't let us reasonably use a ladder of any sort.
What we can demonstrate is basically where is the laser? It's an infrared laser. I'm projecting here a pattern, but obviously it's in infrared range, you can't see the pattern. If you had an infrared camera, like what I do, you could actually move the camera and see the actual infrared colors. If you move it. So you see there are, and if you can come closer, you can see several dots. So these are laser dots here that are projected by Kinect on the particular subject. So here I'm using this corner of the podium. The rest of the space appears black. In other words, there isn't significant presence of infrared light. So what this infrared light is, it's basically a laser that moves in a particular way and creates this pattern of dots, sequence of dots here. And based on the density, location, and the intensity of the color on this pattern, it can reconstruct the depth. So basically, the idea is to move this. As you see, I move now the camera, so the pattern goes away here. So I move the camera that has a projector, an infrared projector on the front, and I can move it here on whatever object I want. And you can see even on the front row of the chairs here in the auditorium that these dots appear as well. So the pattern, the laser, it's a laser, so it goes everywhere over here, and within a field of view, of course. So the goal is basically to move this laser pattern, which is more robust and more rigid, and illuminate with those dots the subject, and from that reconstruct the exact location of each of these points. Now, again, what is the practical problem? It is light. If I go too close here, it's going to be so bright that I can't see the dots. Because all the dots are dense, it's a dense grid of dots over here. I'm too close, all the dots are overlapping with each other, so, well, I cannot see where how to separate the dots here. So the object is so bright in terms of infrared light that, yep, I can't tell what it is. So I have to find an optimal distance again. So here I can see the individual dots. But because of this practical problem, to go away basically from the subject, from the object that I'm scanning, the resolution may drop as well. So as move away, obviously the resolution will go away. So again, we have exactly the same problem, finding the optimal distance from the object so that the resolution is as best as I want. So let me turn off now the iPad view, the infrared camera view, and see what is the actual 3D data that is reconstructed. So instantly, the dots can be interpreted as distance. So I move the infrared pattern, but you don't see here the infrared pattern. You see instead the actual instantly reconstructed 3D mesh, and I'm moving here the view, not the camera. So now I'm moving the camera here. I can approach this object here, and you can see that the approximate location of the distance between the dots that you saw previously are interpreted as location in the 3D space. So in other words, the algorithm moves or interprets the data, the point data that you saw previously, the infrared point data that you saw previously, into actual meaningful location in the 3D space. And what we can do, basically, we can use it either to move around and reconstruct an entire scene or an entire room here in 3D. And in addition, you can show the texture on the top of the surface. So if this is a 3D video, if you will, I can use the color camera that this device has and create the 3D model here of the room. Of course, it's an approximate 3D model, but the idea is exactly the same. If I continue capturing this and coming closer to you and moving it from all different directions so I can capture your back, because right now this 3D video captures only the front of the audience, obviously. If I go back, it's weird because, well, I don't have any data on the side. My camera is on the front. This is why all the data are coming from this direction. But having this part of your silhouette, I can combine it with the side of your silhouette, obviously, if I come closer to you, and maybe top, move around you. And at the end, accumulating this data with the software that the manufacturer provides as well, here I can reconstruct the entire scene. And I think we have some examples online with actual results of 3D scanners like statues from Palazzo Altemps that we can show. How it has been used primarily, although it's a 3D camera and you can see it's a very like instant tool and easy to use as it's shown over here, it has primarily been used to track human skeletons. So basically, if I go in front of the camera, what it does, the red lines here track the positions of my skeleton based on the silhouette that is observed. So basically, I can associate my wrists, or I can even mask the entire background, mask out the entire background or part of it from the, and I think part of the screen is shown here as silhouette here. There you go. So you can mask out basically the actual content and keep only the 3D silhouette of the particular operator, of the particular person, and use a VR superimposed model, for instance, a little cube that I can show you over here. And create basically an interactive embodied experience where you can associate this information of your wrist with whatever you want. It could be something related to the subject that you are teaching, or so intuitively, basically, because it tracks through the depth all this information, you can do whatever you want. So here, basically, I'm simply scaling an object up and down, rotating, moving it, so I can go here, and the object obviously moves with me. So of course, this is a meaningless demo, but illustrates basically how this 3D information could be used in addition to actual 3D scanning. Should we use show the statues? Or,
The time of flight and other laser scanning techniques include actual laser scanning. Two different ways to do it is through movable devices, like the one on your top left. But in museums, this is a project that was undertaken by Smithsonian. It uses a platform laser scanning. So again, depending on the artifacts that you want to do. People have also, and I have the reference as well, they have also explored petroglyph digitization, again, with a laser scanner. And you can see that you can get very accurate results with laser scanning, but it needs to be, the objects need to be relatively big. And it could be considered a limitation or a disadvantage is that it must be carried to the site. So you need to really think about what sort of project you are going to undertake and where it's going to be pursued. Now, something that we haven't, as a team, we haven't quite explored, but we thought we should bring it to your attention, is in addition to object 3D digitization, there is also space digitization. And one of the most successful techniques that has been employed so far is the FARO laser scanner, which basically utilizes pretty much the same technology of the pattern light. I don't know if you can see the dots on the image.
It is exactly the same. It's a laser technique, so it emits light, very intense laser light source, and it observes basically the distance, reconstructs the distance between the actual far recipient, let's say, of this light, the target of this light, based on the time it takes to reach that point and travel back. So there is a very accurate calculator that actually detects this time of flight, and based on that, you have a collection of 3D points. It's noisy in the beginning, and this is not a surface, it's a point, but with post-processing, you can put them together as a surface.
Projects like these and technologies like this have been primarily used by archaeologists, but not necessarily for object digitization for space, so that they can actually scan in 3D the space during the different phases of the excavation. So since there is no way when you excavate something to bring it back to to its original position and status, what they want to do to preserve its pristine quality and also to keep track of all the changes that they performed on the space, they have utilized either FAROS or similar technology to scan their entire space. And of course, that technology is being used by Kinect 2. I don't think we have it with us.
No, we don't have it. It's an extension. It's a second model of the same Kinect technology that, again, primarily was marketed as a human-computer interface to control with your body and a virtual environment, typically an embodied application. Primarily an entertaining application, so something like a game, but it has been used also as a device for 3D scanning. The accuracy has been improved in the second version, and as a result, you can capture smaller details. For instance, of the user, you can see the lips, the motion of the lips, the silhouette of the face, and for static objects, obviously, the quality of the 3D scan is significantly improved to I think 3 millimeter accuracy, or definitely sub-centimeter accuracy.
Now, the last one, that it is the technology and the concept behind the digital epigraphy project, is shape from shading, which is pretty self-explanatory. The way the 3D shape is being reconstructed, it's by observing where you have shades and where you have light. So you can basically reconstruct the 3D shape of either a person or an object.
And before we go to the actual dissemination, or we are going to show, we have one more sensor that utilizes exactly the same laser technology like the Kinect that we saw previously. So this device that I used with the laser points was, I believe, released as a low-cost consumer device. When I say low cost, I think it was $150, something like that. And of course, that's the older model. It has been discontinued then. In 2013 was another model, which is now discontinued. So where this technology goes now, it's getting smaller, more accurate, and it can be embedded in other devices. So from that size, we went down to a smaller camera. To a smaller camera that can be, that's the size of the camera. So it's significantly smaller here, that could be attached to your phone. Of course, you can attach it to iPad as well, but there is a smaller mount if you want to attach it to, let's say, iPhone 6. Now, what this camera does is exactly the same thing. It's the same technology. And that's why we use the infrared camera of this to observe the infrared pattern of the other device. So we used one to understand the other. But the technology here is exactly the same. So it is like having a small Kinect here on your iPhone. So that was released, I believe, in sometime in 2014, if I'm not mistaken. So what happens now, 3-4 years later, we have exactly the same technology embedded on iPhone X. So you don't even have to actually take this. There is a similar technology with laser, basically, an infrared pattern that is, if you enable it, it shows this pattern or this laser the technique illuminates your face in infrared, of course. So you don't get annoyed from this pattern. And the infrared camera observes, obviously, the pattern and reconstructs the shape of your face. And you can use it, for instance, to unlock your phone or to digitize, if you want, to use your phone if the proper app is made and move your phone with a 3D camera now around a device and capture exactly the same set of points and reconstruct the surface. So we, as you can see, there is a pattern. We go smaller and smaller and smaller, and the same technology has been embedded even in head-mounted displays. So this is another product by Microsoft, HoloLens. And what it has on the front, it's an array of these cameras. So basically, I'm wearing these, a set of these now, over here, and I will demonstrate later that as part of the dissemination process. I'm scanning the space here, but not primarily for having the 3D model of the space. You can do that if you want, but primarily to superimpose the result of your scanning. So I may use this, for instance, create a scan of that, and then extract the 3D model that I have digitized and put it here virtually. So wearing this, I can have one on the side of the other. I can move around, and I can see a rigid virtual model of that. I can, of course, scale it up. So if this size is small, I can scale it up. I can make some measurements, and I can use it to perform my study, the study of whatever discipline you relates to this type of 3D scanning activity. So we used archaeology again because the digital epigraphy and archaeology project uses these techniques. But of course, you can adopt exactly the same mechanisms for other subjects as well, other areas as well.
We'll get to that, the structure sensor, when we talk about the statue digitization. But the first objects of study were, as I mentioned before, the paper copies of inscriptions, which are these very descriptive pictures for those of you not familiar with the process. When you have, for example, an inscription on a stone, you can use a particular type of porous paper. You damp it a little bit, and then you press it on the stone. You rub it with a brush. Maria has created some of her own, we call them squeezes. And again, the name is very descriptive of how they are produced. And when you let it dry, you basically have a copy of the inscription that you can then take, you can study. And since the paper is porous, but it is relatively hard, it can also be at least preserved for decades. However, it's still paper, which means that, first of all, it succumbs to environmental conditions, humidity, tear, obviously, wear and tear. And also, there are cases where the original inscriptions are lost. If they are not lost, if this copy was made 100 or 150 years ago, it actually preserves the text significantly better than the text that we actually have now from a stone that has been over the past 150 years outside in the rain and the sun and the humidity and dryness, which means that all the collections of hundreds and thousands of squeezes that are housed in museums, institutions in North America and in Europe, they need to be preserved for several reasons. And additionally, as you can imagine, not everybody has access to them. So if we can make them available online, we can actually disseminate knowledge and give the opportunity to everybody to study them. So far, before we started, the way that they were preserved in a way was either via the typing of the text, which is nice in the sense that, yes, there is a way to preserve the text, but there are several limitations, including the fact that nobody can do a different reading of that. All the lines and the dots that we have here, particularly the small dots on the fourth line there, indicate letters that we think that they were read like this, or we think that this is what we are reading on the inscription. But if you have the actual 3D, the actual inscription or the 3D model of the inscription, you can give the chance to someone else to see whether actually this is the letter or it could be something else, a different word. Another way to digitize them before the DA project was to take pictures, and albeit very inspiring, you can tell that you cannot read much. Additionally, if you don't have the 3D model, you cannot perform any measurements, which is something the same way that we can determine who is the author of a letter by just studying their handwriting. It's the same thing that we can do with inscriptions. We can determine date, location, the scribe or the group of scribes that worked on particular inscriptions, which means that hopefully we can also identify and put together pair fragments. But there's nothing that you can do when this is the form of digitization that is being used. Trying to combine the two before 3D technology was this, an image, and then handwritten what the epigraphist could read. So when we were exploring different methods and we explored the possibility, we had the ARTEC back then, but it cannot do anything with the paper copies of inscriptions, with the millimeter size of the letters. So what we decided was to try a regular office scanner. As I said, we don't have it with us, but it is an actual A4 scanner. What we do is we scan the squeeze twice. We just change direction by 90 degrees, by a 90-degree angle. That way, our algorithm utilizes the shape from shading. So since the scanner projects a light, it captures the letters from that side. Then you rotate your squeeze. It captures the shape of the letters and the inscribed surface from the other side. So based on where the light and where the shade is, our algorithm produces the 3D model of the inscription. And this basically it's done in a matter of seconds. And our project at digitalepigraphy.org, we have most of the collections online. We are still working. We are currently collaborating with Université Lyon 2. And they are uploading a little over 9,000 artifacts. I'm going to show you a quick example. We have a sample here. As you can see, we have experimented with different, including this one is lace, actually, that the UK National Archives wanted to digitize from the 18th century, I think, if I'm not mistaken. We have worked with seals and medals, but this is one of our first artifacts. As you can see, we have a variety of options down and on the side. So what you can do with a 3D model, basically, first of all, you need to use everything, all the additional tools and options that 3D technology offers you, but you also want to keep all the advantages that you have had you had the original artifact. So when you want to read something, let's say that it's not very legibly written, or the lighting is poor, what do? You would try to move it. You would try to find a light source and do this. You would bring it closer to your eyes. You would move it like this. So we tried to keep all the options, the physicality options, the natural physical options here. That's why you can move it. You can
relight it as well.
Translate it, yes. I'm going to do that. You can zoom in, obviously, as much as you want, and you can relight it. We have included options for all the angles that you see. They include natural and unnatural lighting, so both including the option of what you would do had you had the artifact in your hands, really in your hands, and unnatural lighting, so from directions that you couldn't have had in actual life, but can give you, as you can see, different readings. And they really make a difference when we are talking about the sites or which are usually the most weathered. We have options for a 3D. Let me move it. '3D visualization of the original image, and you can kind of tell that this is paper. We have options for the edge map, and again, you can see it captures the edges, which really gives you a very good reading of the inscribed surfaces. You can do a 2D depth map, 3D visualization, and you can, again, you can see how you can use it for, depending on the artifact, depending on how weathered is your artifact or your inscription in that case, and basic 3D visualization. Do you want to demonstrate the sites? The other options?
The non-photorealistic visualization, for instance, the edge map basically highlight different geometric features of the model, and the same for the depth map. So here, what the depth map shows, although it's a flat visualization here, the intensity is proportional to the depth. So the darker it is, the deeper this point is located in the subject. So in other words, the 3D model is kind of converted into an ink-like presentation where in this particular case, the inscribed areas appear darker as if it was an ink, and you can combine it with the 3D model. So here we have the 3D model and the depth map on the top of that. So again, the deeper it is on the model, the darker it appears. And all these non-photorealistic visualization help the scholar in this particular case observe the actual object with more enhanced visualization than what we really can do with a real physical object. And this demonstrates the advantage of having something in 3D on the computer where you can interpret the data in a different way, in a non-photorealistic way, in a different way than what you actually do in the real, with the real model in the real physical space.
You can also demonstrate the measurements.
Yes, and of course, yeah, you can take measurements. For instance, you can measure here the distance between this. Okay, so let me, that line, and it not only takes measurements, but also along this line. Here you can see the groove basically and how this goes up and down according to the 3D reconstructed model. So you see this very small detail along this line, how the mesh basically changes. You can see how the depth varies, and so that's basically the line, that the segment of the line here. And of course, you can find the distance on 2D basically, if I was taking this photograph here, or in 3D, the actual, which is longer because you travel more in the 3D space here. And these are real values, so you can actually make some measurements and use that in your scholarly study. So you can actually use this tool to generate new scholarly knowledge in that particular field that we demonstrate here.
Basically, we do, for ancient inscriptions, we need to do exactly what we do with handwriting and when you are judging someone's style with stylometric analysis. But we can take measurements and date the inscriptions. We can try to see whether, when it is fragmented, if they come from the same monument, or you can attribute it to scribes, etc., which is, again, something that you couldn't do had you had only the 2D image. But it's not only that. If you have if you want to study 500 different fragments, it's going to take you basically your lifetime only to perform the measurements before you are actually, if you are ever actually able, to put everything together and draw conclusions. Now, if you do that quickly in a matter of minutes or seconds, depending on how many you give to the computer, then it gets you closer, one step closer to draw conclusions.
I think we can demonstrate also, or we can do it later, since we're here, the different results from different scanners here that
if you want, we can do that now.
So again, going back to what we discussed, the first scanner that we saw, the Artec 3D scanner.
If you remember the artifact that I had on small
this shows basically an example of using the actual scanner on the. This is a small detail basically, and I think the actual larger object is here. If I can, pull it up here. Yeah. So the noisy scanner that I try to use here. So the actual result, if you spend some time on a object like that, I believe it wasn't bigger than this, you can see the final refined result that was obtained using this first scanner. So as I said, it doesn't go beyond sub-centimeter accuracy. So if there is some pattern, let's say here on this almost flat area, you can't see that pattern. So you have to actually superimpose the image, the colors, the texture to see that pattern. As a result, you experience this as if it was a more smooth version of the original artifact. So what it actually captures is the general structure above the sub-centimeter level, and yeah, you can judge by yourself about the quality of that particular scanner. Again, the technology improves. This was one of the first scanners that Artec created, and a smaller version fragment from the same, again, model is shown here to appreciate better and judge about the quality of the detail in this particular example. And of course, we can still observe the model. Sometimes we understand better the geometry of the model by playing with the light source here. Regarding the flatbed scanner, so in other words, regular office scanner, other samples, like for instance this seal, where we used again an office scanner to digitize coins or objects like that, non-highly reflected coins. So this is porcelain, I believe, the actual material, and actually we can see the picture. Yep. So this is the actual material that was digitized, and you can see the maybe the edge map or the depth map of the actual material here. And another example which is interesting, as Lenny said, is the lace that was a collaboration with the university, UK, the National Archives in the United Kingdom, that they had interest in preserving this lace, several pieces of lace, and the actual 3D digitization captured not only the details, but also the orientation of different components of the lace. So by playing with the light, you can see that the actual detailed orientation in each location was very well preserved. But of course, we have certain limits in the case where there is a discontinuity in the 3D model, so there is a gap basically in the 3D model, like here in these areas where some of the details may appear erroneous. But this is the overall result of the scanner.
And with the coins, also plaster casts of coins work very well if anybody has collections. They are not too reflectant, so you can actually use a flatbed scanner with plaster casts of coins.
And you can, the real use, the real value of a 3D model is that you can actually enhance the shape of the original. For instance, here with an enhanced visualization and relighting, we could actually understand from the shape of this very weathered seal that there are two little lions on the feet of the king here, which is the Henry III of England here. And another example of an even more severely weathered seal is this one. Where by playing with the light, you could, and the 3D surface, you can see that we have two actually figures sitting on this chariot that appear over here, and you can see the hair of the other one. And as you can see, there is a stick over here, and there are two horses. So by playing with the 3D model and the details, you can actually enhance some of the features, and of course, some of them may appear in the 3D model accordingly here in the non-photorealistic. So you almost have an image, a shadow here of the second person, and a better understanding of the details here of the carriage. And of course, these are all sub-millimeter or millimeter accuracy because of the flatbed scanning.
We go back. Give me a second. Other things that we can do if we want to compare lettering techniques, and this is not an option online currently, but we are working towards making it available for everybody, is like I said, if you want to compare lettering techniques for whatever reason, our algorithm can perform automatic letter segmentation, letter grouping, which can lead to basically comparing the letters through registration. I'm going to show you the result over here. Experimentally, we have run experiments on different groups of inscriptions, and so far they have been successful, but like I said, it's not yet an option online. But if you can see, we can get the affinities or lack thereof between the letters. So something that, imagine that if you want to compare 500 different fragments, you couldn't possibly do that manually. I mean, what sort of notes were you going to keep? And we did that for a few sample letters just to make sure that the technique worked. Now, excuse me, case studies, and I'm going to show you results and better demonstrate, hopefully, the significance of 3D digitization and electronic preservation. We worked in collaboration with Cornell, and they had a collection from Monumentum Anchiranum, which is clearly by the name, it's in Turkey. It has on the temple, on an actual monument, it has the res gestae, which is a very important historical document that is written both in Latin and in ancient Greek. It's basically one translation of the other. It's the same document, but in two different languages. Cornell University launched an expedition in 1907, 1908, so really early in the 20th century, and these are actual pictures from the expedition, and they created the squeezes that I showed you before. They were being housed at Cornell, but as you can see, and as I already told you, they succumbed to conditions, dirt, wear and tear, so we wanted to digitize them. Now, issues that you may face, as I mentioned, I don't know if you picked it up, but I mentioned the monument. So when we are talking about squeezes, we are not talking about something that can be accommodated on a flatbed scanner, or at least a regular flatbed scanner. So what we did, we actually created, this is the 3D model from the website. We worked with their team over there, and we tried to imitate the movement of the scanner, the process of the scanner. So basically, they mounted a camera and a lighting source on a type of rail, and they started taking pictures. And then they moved it, and they took pictures from a 90-degree angle, imitating what the scanner is doing. It was experimental, but it actually worked very well. Another project, the one that I mentioned before with the University of Lyon 2, it's the e-stampage, and as you can see, this is the actual, the squeeze. It's on the table, the image, and this is the 3D model, and they are currently being digitized. This is the example on the website. This collection is not yet available online, but it will be, and they come from different parts of Greece. The project that Angelos mentioned before with the Library of Congress, and you can see what they had up here. And the digitization, which was able to give us the name, which was Solomon, something I don't remember.
It's basically a printing house of Philip and Solomon's in Washington, D.C. So basically, you can actually read, if you pay attention here, Philip and Solomon's Washington, D.C. on the bottom.
I don't know if the PowerPoints will be available, but I have the links on our website for everything that I'm showing you. Another collaboration with the University of Berkeley. They had severely weathered squeezes on the Aleshire collection, and this is a 3D model, but you can see, I mean, severely weathered. This is the best that we could get, even with the 3D model. You can see that they had, it is dotted, and we couldn't tell from the actual squeeze whether it was letters or markings meaning something, or if it was just, again, distraction. Most of them turned out, based on the 3D model, that the squeeze was distracted, very badly preserved. This is the original scanned image, so this is what they actually had. This was, and you can play on it on our website, you can see that you can kind of see some letter markings which are entirely illegible on the original scanned image. And we tried with that particularly weathered squeeze, we tried different methods. You can see, again, you can kind of see letters, something that was entirely impossible on the actual squeeze. Another one here. Any questions, anyone, before we move on quickly to the next part? Yes?
Does the intense laser light affect the surfaces?
No. None of the technologies that we have used affect the artifacts in any degree whatsoever. So you can go ahead and use it on anything. And you can find information if you want to, because it's reasonable that museums and collectors are going to be hesitant, but you can find information online that you can show them, even through the companies that sell them, that can guarantee and they can describe what sort of technology it is and how and why it does not affect the artifact.
But of course, you have to share this information with the museum first, that it is a light, although invisible light, that it is a light that you actually project. So if it is a collection that is not allowed to be photographed with regular flash, they may have a problem exposing the object in this kind of light. So it is an information that indeed you have to share with the museum first.
And anyone else? Sorry. Yes?
Any light of the background, does it affect on the scanning or not?
Every condition, outside condition, can affect the scanning, yes. So you need to to have some time, even if you have something like this, so that you can see where you are to place it, so that you won't, even your shadow will not be casted on the artifact. So yes, outside lighting conditions can affect the scanning. It shouldn't be too bright, for example. Obviously, the room, it shouldn't be too dark either. It goes without saying you can't work with behind a plexiglass, so you need to work with a museum to let you remove it from the artifact from its case. So yes, there are different conditions that can affect. Particularly bright light won't let you capture it.
But most of these limitations are really practical. For instance, if it is too much light, well, the technique doesn't work. You have to move away to attenuate the light.
Even if you are taking a picture, personal picture of yourself, if you have the sun hitting on you, it's not going to look, it's going to be blurry. So it's exactly the same thing with 3D scanning, very, very intuitive.
And even simpler things that you laugh, but happens that it has a field of view like a camera. So the object has to be in front of the camera. So if you actually move it like that, obviously it's not in front of the camera. So there are very, very simple issues like that. So you have to actually concentrate and focus on the object, because it is a field of view like in the camera. You have to stand in front of the camera, obviously, to be on the picture. So everything, and of course the field of view is like that always. So it starts from the camera, and it increases as you go far, and you have to account this thing of trapezoidal or cone of the field of view as you move and scan.
From personal experience, if you can use, for example, the structure sensor that we used last, where the person who is actually scanning has also the field of view in front of him or her. That helps immensely. When we did it first in 2013 with the Kinect, I was using the Kinect, but Angelos had to be on the computer, keep telling me, okay, you just lost it. You need to turn a little bit left, which makes it very hard, because you cannot be too close, you cannot be too far. And I'll give you, I think this picture will give you a sense of the limitations. You can't be too far, you can't be too close, but you need the plug, and there are walls. So if you don't have, and over there I can't see anything. I'm holding the Kinect, but I don't see what I'm getting. So if you are trying to do this and you are squeezed, but you don't know if you are getting it, it's very hard to capture even a large artifact, because we are talking about a life-size statue that is also prompted up, if you can see. So even with such a large artifact, it's very hard to get it. It's a lot easier if you can have something where you can actually see what you are scanning. Otherwise, it's nearly impossible, let alone if you are doing something like this.
And of course, this demonstrates the problem with the field of view. So the field of view starts from the camera. As you can see, the little yellow area on the front is the one that does not produce result. So you have to be after that line, and you can see a particular frame of this acquisition here. This is from another life-size statue. And should we show the 3D models?
We had one more question,
yeah.
and then.
I was just curious, from a teacher's teaching standpoint, will the files ever be available to actually 3D print?
They already are. We have it next on our dissemination part, yes. We have, even though usually when you produce a 3D model, people are accustomed to large files that they cannot be accommodated, let alone shared or anything. We actually, what our program, what it saves is the information so that the 3D model is automatically reconstructed on your computer without you realizing it. So basically what you are saving is a regular JPEG image. What you have, as if I was taking a picture of you right now. So they're very small files.
But to answer your question more broadly, independently of this particular project that we are involved with, all these techniques gives you the result in a 3D file format. So there are popular file formats like OBJ, STL, FBX, and you need to have some software. Most of these companies, the manufacturer of the scanner provides the software to open and visualize the latest version of the operating systems. And I'm a Windows user. I know that they have a 3D viewer. So if you find a 3D model from online, you can actually open it on your computer without additional software. And the problem with the actual models that you obtain out of 3D scanning is that you cannot use them immediately directly as is for 3D printing. They have holes. They are not an actual solid object. You may capture the top, and you are missing a small section over here. You have to fill that in order to create an actual solid object without any gaps, without any missing information. And occasionally there is noise. For instance, there could be a 3D little triangle over here. So you can clean it up over there. So get rid of the noise, clean whatever is redundant, and fill any gap you may have. For instance, the standing statue, even if you take everything around it, still there is you didn't get the bottom, obviously. It wasn't, you couldn't lift the statue and take the bottom. So, of course, you can complete that missing bottom part of the model with a flat filling, let's say. So there are 3D modeling tools that assist you with this post-processing, and once you have an actual solid model, you can provide it to the 3D printer. So it's not okay, scan it, here's the file, print it. So it's not that easy process, unfortunately.
And also try wherever you are when you are scanning, make sure that you are there very early in the day or very late in the day so that there are no people around. Otherwise, they get in the field of view, and you may spend 5, 10, 15 minutes to try to do this, and you have to start all over again because that cannot be cleaned out.
Yeah, but I think the problem with the people is that all these technologies are nice, cool toys, and say, oh, what are you doing here? Oh, let me take a picture of that. And so you start getting some
noise. Different kind of noise.
Yes.
We used for the statue collection also the structure sensor that Angelo showed you. Do you want to?
Can we demonstrate it here? I think it's the only technique that we did not actually demonstrate live here. And
we have to move on because time is almost up.
Yes. And if I actually mirror my screen, the frame rate may not be very good,
but in reality, it's actually working very good.
Yes, on my side, it is.
And I'm using this in class as well when we are working with 3D digitization. Students bring their artifacts, or on occasion they scan themselves. And the models are very good. They have also 3D printed them on occasion.
So how this works, basically, it starts scanning and accumulates basically the different points. So I'm actually moving, collecting points, and the 3D model is superimposed on the actual video feed, video image. So it's an interactive process, basically. You see the result, and it tracks, obviously, the space at the same time. So all this white area that is superimposed is what it has been digitized. So I can understand where the gaps are, and I can complete, of course, this model coming on here on this side. And of course, if you are too close, as I said, the red markings here indicate that you cannot capture this area. You are too close. You have to move far away. So it's a matter of also the software that the companies, the manufacturers provide that assist you in this process. And I believe that this is a very nicely done software on their side that gives you all this information. So here, obviously, from the red markings, you can understand that you are too close. And so assuming that I'm satisfied with the result here, I can stop it. And I can observe the 3D model that was captured here. Now, this is the 3D information, but don't forget that we have also a color camera from the iPad. So what we can do, we can observe it, first of all, in different ways. So we can see the actual triangular mesh. So the approximation, basically, of the real object is nothing else but a dense mesh of triangles that cover this surface. So if I superimpose the color view from the cameras, this is a rough approximation, but there is a processing that maps all the consecutive video frames that I took while I was moving around this object, and at the end it gives me a better impression of the 3D model, not because I have more 3D points, but because I have attached the actual texture, the actual colors on the top of the model. As you can see, it's a process. It takes some time. We're now 71%. But overall, as we said previously, it's a matter of understanding the data, understanding the process, be able to use a tool that guides you through that process and warns you when you are out of the field of view, when you are too close. And this is, an example of the result of the 3D model. I should have taken one more picture from here, because right now you see the discontinued color here between two pictures. So if I had spent more time, obviously I could have done a better job. But only from this, like a minute long session, the result is satisfactory for the general purpose. Now, if you want to pursue some scientific study, you may want to have like a sub-centimeter accuracy, and in that case, you may use like a platform with a very rigid scanning process that we are not going to demonstrate today. But for the general audience, I believe that this type of 3D modeling, instant 3D capturing is sufficient enough and low cost enough that you can use with your phone and your iPad as well. Now, the feed that you had here was not very continuous. You saw only pictures of what I was doing, but of course on my side it was a continuous feed, so there was no lag in here, obviously. So it is really helpful for the user.
It's also you are using what you are seeing, so you don't need any plugs. There's no space limitation with that. And when we purchased it first in 2014, it was the price was $500. Now it's $350. So if you are going for a digitization project, it's not something that should be restrictive.
And of course, you need an iPad, which, by the way, all the price of every technology drops. And when this technology was released, the iPad was $500. Now it is $300 as well. The same model.
This is it shows a particular one where we can actually see the grid and the mesh point. And this is These are the results, and I don't want to spend more time on the website, but these are screenshots from the website.
You remember the photograph that showed Eleni moving in front of the sculpture, so using the Kinect technology, the one that I demonstrated previously. So this is the actual result of the 3D model of this life-sized statue. Again, we have captured most of the details, as you can see, that are in the centimeter range, or about that half centimeter range. But the texture, so if there was a small groove on the thigh of this character here, this model, obviously you couldn't capture this sub-centimeter, millimeter scale accuracy. This is why the model appears smoothened out. But of course, you can superimpose the colors from the camera that adds an additional layer of detail from the photographs.
Other things that you can do, the same way that we are studying the lettering techniques, you can also study posture. Or you can study other reconstruction techniques, depending again on your research question, on your research project. But very often we are talking about Greco-Roman artifacts, or a Roman copy of a Greek artifact, or we are talking about Renaissance copies of Greco-Roman antiquity. So how can we start literally studying and quantifying differences, similarities, affinities, or lack thereof between them? We performed a study only based on the collection of Palazzo Altam, the one that we're just showing you before. And you can see that using our algorithm, you can compare, similarly to the lettering techniques, you can compare postures. And if you stand in front of a depth camera, so let's say a Kinect, which is how we did this, you can give a skeleton query. This is an actual person. So you can get the D on top indicates the distance, so basically how close, what are the statues that appear in the same posture with the one that you gave in front of the Kinect on the top left side. And the same way that the affinities, the lettering affinities were shown in the form of a dendrogram, we have the same down here. Again, this particular part, similarly to the lettering techniques, it's not available online, but experimentally it has worked, and it will be available. One of our recent publications that describe the technique. And now going to the dissemination, we are covering, as you can see, pretty much all 3D file formats. And another thing that I wanted to show is usually people have issues with 3D viewer, or if they don't have a good 3D viewer or a 3D viewer at all. So what we are offering, particularly for the DEA project, an HTML tag, which works exactly as a YouTube video. So basically, if you copy and paste that on your website, on your syllabus, or whatever it is that you are working on, you are copying our website.
Even Canvas accepts iframe. Even Canvas, you can copy-paste on Canvas. Things like that.
So if we update something, you don't have the updated version, but you are copying and pasting our own 3D viewer with all the options. And I'll start moving a little faster so that you can get to this. So far, we have over 9,000. Now, we just started a new collaboration with the University of Venice, so it's going to be over 10,000 very soon. To make them even more accessible, you can access them through iPads and other tablets on your iPhones, smartphones, anywhere, which, again, we try to, not to do it fancy, but to imitate and to keep the physicality. We are used to touching things in order to understand and study them. So if you have the option to do all that by actually touching something, even if it is on the screen, it's a lot more intuitively for us, for human beings, to understand, to conceive size and even on occasion shape, even though we are not actually touching the objects. We have worked with 3D printing, but I will let our colleague Sarah talk about that. I just have an example of just one word of one inscription, because when we started experimenting with 3D printing, it was very expensive, and Marston Library did not have their own 3D printer. So we were only able to 3D print this, but now it's accessible. And
Can we demonstrate
yeah, sure.
this?
It is.
I think this demonstrates well the physicality with respect to the iPad. The iPads have a gyroscope accelerometer, so you can actually rotate the iPad and feel as if it was a window in a virtual 3D space. So what it is demonstrated here by intensively rotating the iPad is that you can actually relight the object or observe even some other sides of the objects as if it was, again, in a box right behind the iPad. Therefore, it converts this 2D platform into a little virtual window, if you will, where you have the impression, as you can understand from this interactive, from this descriptive video here, that you have the pseudo feeling that you are holding basically the object. The object is right over there. You are holding the frame of the object, and by moving accordingly the object, the iPad, you are moving not only the object, the light source changes properly, so it relights. You can have exactly the same interaction as if it was a physical object in front of you. In addition, obviously, you can scale it up, scale it down, and interact, browse a collection of objects, something that you cannot do, obviously, in the real world. So the touch screens provide some augmented physicality where you can almost touch the object, but at least you can manipulate it and have the same interaction, the same connection with the object that resembles the natural manipulation of the physical objects.
And the last part is how can you put everything together? And Angelos is going to demonstrate how we've started implementing and including augmented reality.
Obviously, iPads are, more accessible, and almost everybody has now a tablet. If you allow me just a minute to provide you the feed that I'm getting right now. This last demonstration will lead you towards, will gradually basically move the topic towards the 3D printing and augmented reality that Sarah is going to talk about. But we wanted to demonstrate an augmented reality environment with a HoloLens, where basically you can impose on the 3D space the result of the 3D scanning. So what I have done here, I have put over here, just in front of me, the 3D model of an actual, and we lost it. I'm sorry, the connection is not stable. Let me try that one more time. So what I have positioned here in front of me, and I get a mixed reality view, so I can see through the glasses. These are transparent glasses, but at the same time, I can manipulate objects. For instance, I can hold this object and I can put it on the top of this bench because I want to compare it with the other real object. So right here, I have both of them, one on the side of the other, and I can. I'm sorry, the connection. It basically tries to connect through a live stream that I'm having on the computer, basically, of this device, the Microsoft HoloLens. Let's try now. So what I have here, it's a mixed reality view where I have a real object on the side of an actual, of a virtual object, and I can scale it, for instance, as I wish. I can rotate it, and I can perform, intuitively different through a set of gestures, some manipulation of the virtual object and have, again, the same kind of interaction of physicality as if it was an actual object. I have a collection, actually, of part of the library. So here is a bust from Rome, and here we have the 3D model of a lion, and I can actually move around it naturally and observe it from different sides. Yep, it's over here, actually. I can take it and carry it with me and put it maybe on the front seat over here. And maybe I can scale it up if you want here, so I can or of course change the orientation and yeah. So let me actually rotate it. Yep. Okay. So here's my lion, and of course I can move with respect to the room here. I can observe different sides of that. And all this rigid interaction, because it is rigidly placed within that room, is because I have Kinects on the top of my device. So actually, you can you are scanning the entire space, so you understand exactly where you are located within the 3D space. And at the same time, you can superimpose on this mixed reality view objects that you have previously digitized. So what we're showing case is basically the entire pipeline from generating the data up to actually using the data either through web platforms, tablet platforms, or even later in the future with augmented reality platforms like these that are going to get obviously more affordable and will be more approachable for everyday use. And some scientists forecast that instead of cell phones, we will have a small, tiny little overlay on our glasses that we will use, of course, not as cumbersome as this one, but the technology gradually goes there and this demonstrates well this physicality. I have it here in front of me. I feel that I can almost touch it, and through this mixed reality view, you got a glimpse of how it feels to basically have this visualization in front of you.
The limitation is that you can get dizzy while you're using it and after. That's why I can't do it. But this was all from us. So how you can get from paper, from the paper cast of the stone inscription to the 3D model, and how you can get from other artifacts to studying their posture, and all the way to 3D printing with our colleague, Dr. Sara Gonzalez. So thank you very much for your time. And if you have any questions, feel free to ask us now or during the break. Thank you.
I believe we have 5 more minutes, either for questions or if you want to actually try, for instance, this, which is very easy to you, and try to scan this by yourself. We do have 5 more minutes. So, who wants to try it? It's really easy.
Maria is actually looking for 3D digitization techniques
press
for her
scan
dissertation.
Yep, that's it. So it accumulates the points gradually. Yep. So